Welcome back to 8701. So we start a new chapter now, QCD or quantum chromodynamics. And in this first lecture of this chapter, we talk about the production of hadrons. This is really meant as an introductory lecture, but we will also already see some very interesting and useful concepts. So we want to produce quarks and antiquark pairs. And we do this in electron-positron collisions. We have studied in detail this first part of the diagram already. Specifically, we calculated the cross-section of muon and anti-muon production, and we also have seen what changes then we have same-time particle in the final state, so the electron-positron scattering to electron-positrons. So now we replace the muons with our quarks and antiquark pairs, and it's, as a first step, we want to remind ourselves of the available quarks in this discussion. So we have the up quark, the down quark, charm, strange, top and bottom. You see that the charges are given here and the photon couples to the charge. So the charge is not 1, but it's either 2/3 or -1/3. We have also here in this table masses given for those particles. They range from a few MeV to 173 GeV for the top quark. The bottom quark is about 5 GeV heavy. Remember, when we discussed renormalization, we discussed that those masses are not fixed parameters, but in our perturbation theory, they run like the couplings one. So this might cause some difficulties later on. Okay, so now we want to produce an up quark and an anti-up quark in these collisions. What happens? So in our collisions then, we produce those particles. So let's say there's an up quark and an anti-up here and then a plus or minus collision. Those quarks only live for a very short time or travel a very short distance in space, about 10 to the -15 meters. And then they start to pull in out of the vacuum gluons and quarks and antiquark pairs, and those then form into the actual hadrons after some time. And those two pictures here, they look very much the same. The difference is in the way we treat the hadronization, the actual fact of forming hadrons. In this first picture, we are thinking about clustering energy particles together and that way form hadrons. In this picture here, we connect them with so-called strings. And those are two different ways to model and model the production of hadrons. Remember, when we look at this process here, we are looking at very low energy kind of, or lower energy kind of phenomena. And at lower energies, the strength of the strong interaction, the strength of QCD, is the coupling is in the order of 1 or can be larger than 1. So perturbation theory is not possible. That's why we need specific models. This is all I want to say at this point. We come back to this discussion later on. What I actually want to discuss is what we can learn out of measuring cross-section of hadron production. For example, by comparing directly the cross-section of quark-antiquark pair production with the cross-section we just calculated for muon-anti-muon production. And experimental results are given here. So you see as a function of energy, here from 1 GeV to 7 GeV center of mass energy, and in the lower plot, just continuing from about 10 to 60 GeV. What you see here is that there is a rich structure. So you see those resonances here. And you also see that there seemed to be some sort of increase in the value of this ratio. So how can we now understand this? At leading order, we can just write this down. We just calculated the cross-section for electron muon scattering, or for electron muon production. And we can write this very same cross-section at leading order for quark-antiquark production. What we find as differences is the coupling itself. Here we have to use the charge of the quarks and not the charge of the electron. So there's an additional factor here, 1/3 or 2/3 squared. And then there is the number of possible quark pairs which are available, and that depends on the number of colors. Remember, each quark appears with 3 different colors, so we have to account for this factor. All right, and then we build the ratio, and the ratio, everything just canceled out. Great. So we have just the number of colors times the sum of the charges squares of the quarks available. What do I mean by the quarks available? As we go from lower energies to higher energies in this plot here, the kinematic, the energy is sufficient to produce particles based on the masses available. So we find that this explains the step function. Let's look at a specific example. So if we look at center of mass energies, which are larger than 2 times the mass of the bottom quark, and maybe lower than 2 times the mass of the top quark, we are in this specific regime here. And you see this is almost flat, and the number we get is almost 4. Okay? What we get from this leading order calculation is 3 times 4/9 for our up quark, 1/9 for down, 1/9 for strange, 4/9 for charm, and 1/9 for our bottom quark. Okay, so we built the sum here for all quarks which are kinematically available, and as an answer we get 11/3. So this is in very good agreement at leading order, very good agreement with the experimental results. 11/3 is almost 4. Excellent. So this is clear indication, experimental indication that this color factor here is a real thing. There seem to be 3 up quarks, 3 down quarks, 3 charm quarks, and so on. And we also see that this leading order effect here, the leading order calculation, is already very precise. And the reason for this is that this process here is a QED process. So the production cross-section is a QED process, as we just discussed. So now why do I actually have this as part of our QCD introduction? First, you learned about the color factor here, okay? And second, there is indeed corrections. And one of the corrections is the one where you actually produce a real gluon in the final state. And those corrections can be calculated. If you go to higher order, you get a correction from this radiated gluon. You also get corrections which look like this, vertex corrections, and you find that the correction here to R is about 1 plus alpha S at a specific scale over pi. Now at a reasonable scale, this is then, about 0.1 is the value of alpha S, and pi is 3.14, and so you get about a few percent, 3% correction to the R value. Great. Why is this so important when it's a small correction? It's a percent or few percent level correction. What is really important is that this process here can be used in order to demonstrate the existence of gluons. And so gluons have been discovered this way. And the way this was done is by producing E plus E minus collisions and detecting 3 bunches of particles, 2 from the quarks and 1 from the gluons. And then to identify that this gluon here is actually a gluon and not some other particle, one can look at angular distributions, one can identify that this is a spin 1 particle, and so on. So there's a little bit more work needed beyond just showing that there are 3 jets, but identifying this kind of topology in E plus E minus collision led to the discovery of gluons in this kind of collisions. So that was my introduction. As a next step, we now want to have one more step of how can we learn about this kind of structures before we then dive into Feynman diagrams or Feynman calculations, Feynman rules for QCD.